Good afternoon.
Good afternoon, sir.
Any questions? Yes. Yes. 10C. All right. Let's have a look. Polynomial. All right, so here's this polynomial class. So first off, when you look in the constructor here, notice this funny syntax that we had never covered. So you see it says double and then 3 periods. What that means is that the parameter that the polynomial constructor gets is an array of doubles. So it's as if we had written double with the brackets. And from the point of view of implementing the method, there's no difference between the 3 periods and the brackets. But from the point of view of calling the methods, it's a little bit different. So if you, let me get some paper here. If you call a method that's declared as double brackets in the normal way with some parameter, then the way you call it is you give the name of the method, and now you have to put in some array. So you might declare double brackets some array equals, and now you could initialize it with a few doubles. But if you declare the method by using the 3 dots, then you can call it in an easier way. Then you can call it by saying the method, and now you simply put in the numbers without having to put them in an array. So I could say 3.14, 1.41, minus 2.7, as many or as few as I like. That's called variable number of arguments. Or sometimes you see it called as var args, which is a short way of saying variable number of arguments. What goes on behind the scenes is that the compiler packages up all the numbers that you supplied in the parentheses and puts them in an array, and then the method gets the array. The reason I chose that in the polynomial class is just to take out the tedium of making a polynomial object. So if you look at the tester here, you'll see here when I make these polynomials, I just put in the numbers, and I don't have to make an array for it. It's not really a big deal. I didn't want to make a big deal out of it, but I just want to make sure everyone understands the syntax. All right, so now let's see what we're actually supposed to do with this thing. Okay. Actually, this thing has a bit of functionality. Let's make a polynomial. And what was the example we had here in the tester? Well, let's do this one here. 10x cubed minus x plus 2.5. So then I would have to give 10 0 for the squares, -1 for the constant term, no, sorry, for linear term, 5 for the constant term. Here's my polynomial. And now I can do something with it. I can evaluate it at a point. Let's see what it is at the value 10. And it says it's 9,995. Well, of course. Let's see. 10 times 10 cubed. Yeah, that's 10,000. Minus 10. No. Oh, I'm not doing the same one. Which one did I just do? Plus 5. I did plus 5 and not plus 2.5. Sorry about that. So minus 10 plus 5, and it evaluates it. When you look at how it evaluates it, so I show you where I figured this out. There's a standard method of evaluating polynomials called Horner's method, and the benefit of using it is that you don't have to compute all the powers explicitly. The powers get computed implicitly. So look that up if you're interested. You don't strictly have to understand how this method works to solve the homework, but it actually does help. So it's worth looking at it. So now the first assignment is to compute the sum of the coefficients. So the sum of the coefficients is simply the sum of all of these values. I'm assuming you're not asking about that one. Does anyone have questions about how to compute the sum of these coefficients? Yes? But I'm going to give you a tantalizing hint. You can compute the sum of the coefficients in 5 characters, not counting the return and the semicolon. So give yourself a pat on the back if you can figure out how to solve the sum of the coefficients in 5 characters, meaning you're putting 5 characters of your choice at this spot, and without even having to have a loop. For alternating sum of coefficients, one would like them to think that you only need 6 characters, but you actually need a few more to adjust for the sign. All right, so ponder that. But you can also do it the old-fashioned way by simply computing the sum in a loop. It'll also work. Now, what everyone probably wants to know is, how on earth are you going to do pretty two-string? And so if we look at some of the test cases, we need to look at final. So here we have the 10x cubed minus x plus 3, and it prints out, as you can see here, 10x cubed, and the cube uses that pretty little superscript 3 here, minus x, so the squares are not printed because the coefficient is 0. And then it prints the plus 3, just like how you would write it down in mathematics, right? You've all had polynomials somewhere in 10th grade or whatever, and that's how you would write them. You would not yourself write all the terms with a 0, and you wouldn't write -1 times x. You would just write it in this condensed form. So someone asked, what about the 10 here? So let's step back a little bit. Where do these funny numbers come from? So these are special characters that exist in Unicode. So when you looked up this table here of all-knowing friends at Wikipedia, then you'll see that the powers here, the x's are just there for decoration so that you can see it better. The powers are here with these various Unicode codes. So let's, for example, see how we would do a 2. That would be 00B2. And let's actually try this out in here. No, sorry, I have to put a U in here. And now when I say what's in 2, then you can see here the superscripted 2 appear. So let's do the 4 because it's a little bit different. So that's over here. That would be 2074. And now when I type 4, you'll notice that the letter 4 appears here. Okay, how do I do a 10? Now when you carefully look here, you'll see that no one's giving me a 10 as a single superscript, so I'm going to have to put it together from a 1 and a 0. Well, a 1 is 2071 followed by 2070. Oops. And so here, let's see if I did this right. I did not do this right. Now it shows I0, so I must have messed up. Oh, that's because here it really does say I, and the 1 is over here. So the 1 is 00B9. Try this again. What was it? 00B9. Yeah. And now here I do get the 1 and the 0. Side question: why are they so spread all over? Why do we have the 2, 3, and the 1 over here, and then the 0 over here, and then the xi, and then the 4, 5, 6, 7, 8, 9 here? At vastly different places, right? Look at these ones are at 00B something. These are 207, far, far away. What happened? So you can see traces of the evolution of character encoding here. These ones here were a part of a 16-bit code. Notice that it's less than 255, so it still fits in 16 bits. And so at one point, someone designed the 16-bit code where they had a bit of extra space after they tossed in the accents and so on. And they put in a few symbols, such as they said, well, maybe someone wants a superscript 2 or a superscript 3. And later someone said, well, I have even more space, how about the superscript 1? But then they ran out of space. They packed in other stuff in there. And for about 10 years, nothing much happened. And then Unicode came where out of a sudden, instead of having 256 symbols, they have 200,000 symbols. And then they find extra room to put in the others. So that's why they are at different places. Now, they could have duplicated them, but that would have been a nasty thing that gives people choice that you don't want. So here they are at these oddball places. Now, that's all good and well, but it doesn't really do us any good because you have to be able to do this for any number. I can fiendishly give you an array x to the 12,739 plus 1, right? I would just have to make a test case that contains as the input a 1, 12,900 and whatever 7 zeros, and another 1. It would be within my powers to produce such a file. I would probably write a program to produce it because it would be boring to do it by hand. And so you have to be able to format any old numbers with these itty-bitty characters. There's no routine anywhere in the Java library for this because this is kind of a crazy specialized thing to do. So in order to do that, it kind of helps to know how one can take a... Well, okay, there's two different approaches just to solve this. So let me, again, make very clear what it is that I want to have solved. So in my problem is I have some integer n, and out of that I now want to have a sequence of these tiny 0, 1, 2 to 9 characters whose numeric value is n. So for example, if n is 13, I want to have the sequence B9, B3, there are two different ways of doing it. The one way that I could think of is where you turn this string, this number here, into a regular old string. Well, how do you do that? Yeah? So I have this number, the number 13, and I want to turn it into the string that contains the regular, not the superscripted. Well, just these two characters. So how do I go from the number to the string? Someone said toString. Can I do this? Not in Java. Why not? Numbers are not objects, and I can't call a dot on a number. It's unfortunate, but I can. But there is another way. Oh, well, I'm glad we're having this little chat here. If you concatenate a number and a string, or a string and a number, the result is a string that contains the digits of the number concatenated with the other string. So when I concatenate with the empty string, then that gives exactly this. So in general, if you have an integer n, and then you form concatenation with the empty string, that will give you n as a string. Let me try this out here in my live coding environment. I'll use a bigger number for fun. So if I just print n, notice it's an int. And if I do double quote plus n, then notice it's a string containing those 4 digits. So that's good, except it contains the wrong digits. I want it to contain the crazy Unicodes. How do I do it? Same. What do you mean same way? I've taken the empty string and concatenated with n. I mean, there's no other way of concatenating the empty string with n. Well, let's go one part of the way. Let me first of all give this string a name. Str. So now str contains these digits. And now look at come on. What did I just do? So notice that I replaced the regular digit 1 with that that superscript character. Well, how do I deal with the 7? So clearly I can do this again, right? Seven was 2077. Okay. So if you do that for all characters, then you'll get that replacement. And so you could code that as a loop if you first put all of the characters together into a long string. And that's probably a good idea. So let's, 0 was 2070. B9. B2. B3. 2074. $20.75, $20.76, $9. So now here I've put them all into a single string. So now let's iterate over the string. Length. I plus plus. I guess this is going to be a little hard in this live coding environment, but we'll try anyway. So I'm going to take the string and replace it with stir.replace. I also need to have a string of all the regular digits. And that's just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I want to say stir equals stir.replace. Okay, I replaced the all regular digits substring I to I plus 1 with all digits dot substring I plus 1. Oh, phooey. And now stir has become the superscripted one. So that's one way of doing it. So you turn the string into the number into a string, and then you make 10 replacements. I'll show you another way to do it just for fun, because it explains how inside Java how this processing step from here to here was done in the first place. I mean, how does a computer turn the number 13 into the string 13? So here goes. So when I have a number, and let's say, I'll use a bigger number. I'll use 1729. And now remember, when you form n divided by 10 and n mod 10, what that gives. N mod 10 is the remainder that gives you the last digit. When you divide, it gives you everything but the last digit. You can repeat that process, so you can capture the 9, and we'll see in a minute how to do that, and then you can divide again. Well, the next time you do that, the 172 turns into a remainder of 2 and a quotient of 17. The next time you do that, the 17 turns into a remainder of 1 and a quotient of 7. And then the final time, you'll get a quotient of 0, which tells you that you're done, and a remainder of 1. And you'll notice that you get the digits in reverse order. So now we can put those together by just concatenate them in the right way. Oh, and to turn a single digit into a string is easy, because all you do is you make a string that contains all 10 digits, and you do a substring to pick out just one of them. So that part is easy. Now we just need to concatenate them in the right order. This is going to be long enough that I will actually want to write a little method to do that. So inside here, let me put a little helper method that says number, well, let's say int, because it has to be an integer, int to string. So the idea was, like I said before, we loop, say while n is greater 0, digit, we get the next digit, and now we need to do something with the digit. We need to concatenate them up. So we'll have some string result. I'm guessing it starts out with the empty string. We'll figure that out in a minute. And now I'll say, I can probably just say, I can just concatenate here, right? But I'll do it the hard way. Does it come first or last? We'll think about it in a minute. So that's my digit here. And, okay, now let's look at a situation where I already have the string 9. And now I'm being handed the digit 2. So it looks like I need to put that in front of the existing one. So that would mean that it looks like it would look like this. Let's try it out. I'm missing returns here. Return result. So I can call this method here and sweet success. Here's the result, the string 1729. Okay, now I realize that's not the one that I actually wanted, but that's only because of my choice of substrings here, of digits. If I use different digits here, then it would pick the right one. So all I have to do is put in the digits that, those funny digits, and I'll just demonstrate it by putting in one of them. You'd think by now I remember, but I don't, 2079. So now I'm just replacing the 9 and leaving the others in place for now. What's that? Oh, how many characters are this? Yeah. No, there's... maybe I didn't understand you.
Well, I meant, like, is there a quicker way to just change all the numbers to string or character?
I'm just demonstrate here's what I did. I demonstrated how the conversion from integers to strings is actually done inside a computer. So the computer will do this repeated division to find out the digits one by one. It really will do that to do a decimal conversion. And then I said, well, now that we've done that, it's now easy to convert it to any other way of writing those 10 numbers. And so if I want to write them in the funny superscript font, all I have to do is replace the regular digits with those digits. So I'm about to demonstrate that. So let me call this method again with 1729. And now when you carefully look at the string, and I know it's awfully small and I can't make it bigger, you'll see it has a 172, and then it has a tiny 9 because I chose for the 9 this particular symbol. You can put any symbols here you like, right? Maybe you've always felt that a 0 should actually look like a Z, and a 2 should look like a T. And with this unconventional choice of digits, this function will still work. I'll use 17290 to demonstrate my new 0. And you notice now it's 17T, funny looking 9, and the Z. So those are the symbols. And, this is probably a stupid choice of symbols, but as you know, that in different places in the world, people do write the digits in different ways. So we call them the Arabic numerals, but if you look like how the Arabs write the Arabic numerals, they write them quite differently. So you'll see them down here. So they'll write the digits in this somewhat unusual way, or at least for us unusual. So what we call Arabic numerals are not actually Arabic numerals. The real Arabic numerals look like this, and probably they call them Roman numerals or something. No idea what they call them. So here you'll see digits in some Indian language. And so if you replace the string with whatever digit pattern you want, you can extract the digits any way you like. Well, I hope you found that enjoyable, if slightly useless. So now you have two different ways of solving what is probably the hardest part of 10C. We'll go back to the other part. The other part of 10C is really more boring than anything else. It's clearly easy to suppress the 0 coefficients. Right? When you find a coefficient of 0, you just don't print the 0, you don't print the x, you don't print the superscripted number. What I found tedious when doing it was suppressing the minus signs for, the plus signs for positive numbers, and dealing with those special cases in the last two, the integer and the constant coefficient. And I made myself a sequence of like 20 test cases, and it took me a good 15 minutes to beat out all the last bugs that I had in that, because there are so many possible combinations. You might have, minus x minus 1, minus x plus 1, just minus x, just no x's, x squared minus 1. And I was surprised how many errors I had in that. I thought I had an ironclad logic when I first wrote it up, and I found like 3 separate minor errors in adding or not adding in the right thing. So make sure that you build yourself a good test suite for that, because I have one, and I think I will find every last error in your code with mine. Did I beat this to death? Or did I manage to bypass what you were after? You were asking the question, right? All right. Okay. Oh, by the way, on Wednesday, I won't be here. I will be lying at home recovering from something horrible. But there's going to be someone here to give the lecture, and I told her she should spend as much time as you guys want on homework questions. But you'll probably have to bug her about it and ask her. She is looking at the homework as we speak. Any other questions? Yes?
For homework 9C, were we allowed to use our
You were 9C. That I don't remember. Yeah, but you didn't need to.
But you're okay if we did, right?
Right. Here's what I thought you were going to do. So this was the one where you're supposed to print the number of distinct non-empty substrings. Oh, so the issue was the distinct ones. How do you know if a string is is, oh, I see. Okay, what is the advantage of using an array list? So that way you can tell whether it was already found? Ah, I see. I've forgotten to put my solutions up this morning. Someone remind me to do that. I did not do that, so let me see if I can. It's been a while. So we have a way of generating all substrings, right? We did that last time, or actually a week ago. The print all substrings method. If you don't print but you just process them, you get all the substrings. So the question is, now you have a substring, and you want to know whether it was repeating. Oh, that one's easy. So the question is, so I now have some random substring. That one is probably not a good example. Let me do it different. I have now chosen to extract this substring from I to j, and I wonder, should I count it? Right? So I wouldn't count it if it was a repetition of some other substring. Well, I have the string here in my hands, so I can call index off. Index off will give me the first index at which it appeared. Suppose that index off tells me it appeared here. Okay, so index off returns to me an index k, saying, hey, that string did already occur. And now the only question is, which definition of repeating? Anything with overlaps? Doesn't say anything about overlaps, right? Oh, outside the substring. Okay. So now I need to find out, does it happen outside the substring? So I do have to worry about overlaps. So now I have to check whether k plus, oh, how long is this string here? The length is always the difference between the from and past to. So I have to check whether k plus the length, that's j minus I, whether that is less than I. If so, then it was repeating and I should not count it. If not, it wasn't repeating and I do count it. So there's no need to store the extra strings. Yes?
Otherwise, it is last index up, and then I just set my reference point.
Okay, so you used last index off instead of index off. You know, that might actually be smarter. Because if you used last index off, and yeah, that's a much better way of doing it. I hope I actually did it like that too. Thank you. So let me explain that idea real quick. So what he says is, let's suppose that we're looking at this substring, goes from I to j. And now we call last index off on it, which is exactly like index off except it finds the last match. And if last index off said the last match was here, then you say, I'm just not going to count this one. Well, you might say, how am I ever going to count at least one repetition? Well, eventually you're going to find the one that's sitting here and you'll count that one. Now let's say last index off said it was here. Well, that means that last index off finds exactly the string that we're currently holding in our grubby little hands, and that means it was the only one, and we do count it.
That's why I set the last index up, like the reference point you set it.
Yeah?
Like a string behind the string.
Oh, you could also do that. You could, yes. Yeah, but you didn't even have to do that. You could take last index off, and you could check, does it come after this point? Either way. So, so the key is you don't have to store the strings. You can simply make a lookup and compare it to where the current string is located. Now, in this case, if you didn't do it the other way with the array list, there's nothing. I don't think the grader would even notice. The grader is not aware of exactly when we introduced array lists. So I wouldn't worry about it. Other questions? All right, let's move on. Guess we're supposed to have a lecture too. Go away. All right, so first of all, some mildly tedious thing. So remember I just said that in Java, numbers are not objects. You can't call 13.toString, and that's a technical limitation that's there for, I guess, historical reasons. At the time when Java was invented, they knew that they could have worked around that, but they were in a rush and they just didn't do it. And so now we're in the situation that every once in a while you have a situation where you want an object, but you have a number. And that hits us home with array lists. So when you have an array list, and you have this brackets where you need to put in the type, again, for historical reasons, this type here must be a class type. You can't put an int or double here. And so they had to come up with a way of wrapping integers and doubles into classes, and that's what these wrapper classes are. So when you form an array list, it has to be an array list of uppercase double. And then what it contains is not numbers, but it contains objects of this type uppercase double. And all uppercase double is an object that contains a lowercase double. So it's not terrifically interesting, and it's a bit tedious, but one just has to do this. So there are 8 wrapper types for each of the 8 primitive types. And to make this a little bit less tedious, there is this mechanism called auto boxing that automatically converts between primitive types and the wrapper types. Would it be nicer if that called it auto wrapping? Because after all, those types are called the wrapper types and not the box types, but there you go. So when you have on one side of an expression a lowercase double, and from the other side it becomes clear that it expects an uppercase double, it'll automatically apply the constructor and do the wrapping for you. Conversely, if on one side there is an uppercase double and on the other side there is a lowercase double, it'll automatically do the unwrapping for you, which means that in almost all cases, you don't really have to worry about the distinction between uppercase double and lowercase double. So it works even with fairly complex expressions. So over here, if D is an uppercase double, then the plus is not defined for objects. You can never apply plus to an object. So the compiler will unbox this thing, fetch the lowercase floating point number, add 1 to it, and then it realizes, oh, now I have to put it into another uppercase double, and then it'll wrap it again. It's not something one thinks about a lot. It just happens pretty automatically. Every once in a while, there's a situation where it gets you in trouble, and I'll try to show you one just so you recognize it. So anytime that you collect numbers in an array list, you must use the wrapper type. So here we use uppercase double. And after you've declared it, you're pretty much home free, because when you add a value to it, you just add it as a regular floating point number. Don't worry about the wrapper type, and it gets auto-boxed into the wrapper. When you get it out, then here, yes, it's an uppercase double, and then you just put it into a lowercase double. So it's pretty inefficient to do this, of course, and so you would not want to do this with an array list of 100,000 floating point numbers. In that case, you probably do want to use an array. So if you do number crunching of large amounts of data, then the array list isn't going to be your friend. But let's face it, in 46A, that situation will never arise. So you can use array lists of doubles anytime that you want the comfort of an array list. Just to remind you, why do you want an array list? It grows on demand. If you don't yet know how many elements your array list is going to have, then always, your collection is going to have always use an array list, because you can just keep adding things in it and expands and expands. For example, your colleague who used the array list to look whether there were repeating strings, what he undoubtedly did is every time he found a string, he dumped it into the array list. And then when he found another one, he went through the array list to check whether it was already in there. At that time, you don't know how many strings you're going to get. So if you were to use an array, that would be super inconvenient, because you don't know how big to make that array. An array list is just fine. And the same thing with computations of digits. It's oftentimes, of numbers. It's oftentimes more convenient to use an array list. Don't worry about the inefficiency. All right, so yes, let's just do it for the heck of it. Thanks for the reminder. All right, so let's work through this here. Number 4. What's wrong with number 4? Or more elementary. What is very, very wrong with number 4? The brackets, right? You can't use the brackets with arrayless. The brackets are with arrays. What's wrong with number 2? Let's actually try that. Because when I first looked at number 2, I mean, it seemed plausible that this should kind of work, right? Let's see what happens when we do this in Java. So I set up the array list here, put in an element so that it won't crash. Unexpected type, required variable, found value. So the problem is that values.getZero is the value that the get method returns. It's a number. And you can't plus a number because plus means you have a variable, you fetch the value, you add 1, and then you put it back into the variable. So the putting it back part is an integral part of what plus means, and so it can't be applied to something that's not a variable. So that's... Now here we're trying to bypass this, but this is obviously bogus, right? Because over here we're having, again, that sub-expression in there that doesn't work. So this is really the only way you can do it. And so you have to fetch the value, you have to add 1 to it, and then you have to set it back. And so this is the one case that's kind of the worst case of wrappers. Because if you had an array of doubles, a plain old array of doubles, so let me show you that. I'll just make myself a regular array, V's. In this case, I can perfectly well say V0++. and you'll see it increments v0. So only in the case of plus, plus, and minus, minus do you see the inconvenience of the wrappers. Okay, number 2 of today's lecture, the enhanced for loop. So it very often happens that you have an array or an array list, it doesn't matter, and you want to simply look at all of the elements in that array and do something with them. So here's like a typical example, forming the sum of values. So what do I want to do? For each element, so if you were to write this down in pseudocode, you would write for each element in values, and then you say sum plus equal element. Right? Because when you think about it in a pseudocode level, at a higher level, that you say, I just want to get each of the values in turn, and you don't necessarily think about let I be an index that starts at 0, fetch the 0th, increment I, and fetch the first, and so on. That's implementation, that's mechanism. You just want to say, I want to traverse all of the values in this array. And because this happens so often, there's special syntax for this. So here values is an array. Here we use a for loop, but we don't use the for loop with the 2 semicolons. Instead, there's a colon in here, and you mentally read the colon as in. And over here is the variable that is set in turn to each of the elements, the 0th, the 1st, the 2nd, and so on. And then you can use the element in here. So you would read this for each element in values, do this particular computation. So it saves you from the tedium of having to say I equals 0, I less than value dot length, I plus plus, and to fetch the thing out here. So these 2 lines here, not counting the brace, these 2 lines are subsumed in this 1 line. Less to read, less to write. So you should use that enhanced for loop every time that you have a chance to use it. And I do remember the first time when it came out, it was added to Java a little bit late. I got really excited every time that I was able to use it. I said, thank you. Because it was, less tedium. Less tedium is always good. Of course, you will be able to pass this course if you don't do it, but it is a good idea to make your code easier to read, easier to write. Notice that, let's see, do I have this here? No, I don't. Notice that there is a slight difference in the logic. Over here in the traditional loop, we have I, the index, and the index assumes values 0, 1, 2, 3, 4, 5, and so on. Over here, there's no I to be seen because it's mechanism, but instead we have an element, and the element does not assume 0, 1, 2, 3, and so on. It assumes the actual values. So if the array contains, say, 1, 4, 9, 16, at position 0, 1, 2, 3, then the element would be set to 1, 4, 9, 16, and so on. So the index is completely bypassed. You simply get each element. It works for arrays. It works for array lists in exactly the same way. So here with array lists, I have an array list of accounts, and I want to visit each account. So for each account in accounts, here I use the account and do something with it, like get the balance. Here I'm computing the sum of all balances. If I were to write this as an ordinary for loop, my I would go from 0 to... see, with array lists, it's different. You have to remember that it's dot size and not dot length. With the enhanced for loop, you don't have to worry about any of this because you're not programming that little detail. I'm sorry? No, you are confusing something. With arrays, it's dot length without the parentheses. With array lists, it's the size with the parentheses, but you're giving me another selling point for the enhanced for loop where you don't have to even remember this. Right? With the enhanced for loop, you just say what you want. You say, let me run through all of the whatevers. And it doesn't matter whether the whatevers come out of an array or out of an array list. Now, there are two limitations to the enhanced for loop. The first limitation is that you can't ever change an array or an array list inside an enhanced for loop. So let's say I want to set all of the elements to 0. I can do that with an ordinary loop. Over here you see it. I have the ordinary I, it goes from 0 to less than the length, and then I set the ith one to 0. Works fine. But if I try to rewrite this one here into an enhanced for loop, then here I have that enhanced loop. I set, that would be the analog, right, to set the element to 0, but it doesn't work. It'll compile, but it'll run, but it'll do something useless. It'll make element visit first, be assigned to, in turn, the 0th, the first, the second element, and so on. Afterwards, element gets set to 0 each time, but since we're not using element, that's forgotten. And so the result is that nothing happens except some busy work. The array is not changed. So just keep that in mind. You can never use the enhanced for loop to modify an array. Yeah?
In this class, don't you get references? So won't you be able to...
Oh, sure, that's different. So let's say that you wanted to add interest to every bank account. So you could certainly do that. You could say for, yeah, that's a great question. Let's say I have an array of bank accounts. Now I can visit each bank account and deposit $100 in it. I can absolutely call a method, and so I can modify the bank accounts. But notice I'm not modifying the contents of the array. The array contains a number of bank accounts, and after I'm done, it still contains the exact same bank accounts. So the array hasn't changed, but yes, the individual bank accounts have changed. Yeah. So what I couldn't do, for example, is replace every overdrawn account with a null. That would change the array. But I can perfectly well modify the objects. So, and that is a subtle point, because you have to remember there's two levels of modification. There's your array that contains references to bank accounts, and then there's each of the bank accounts. So this one here can't be modified by an enhanced for loop. These guys here, sure, you can do anything you want with them. Yeah, great question. All right, so let's have a look at one. Piazza has run away. Yeah. All right, let's see here. So for each element here, we're printing the element, we're printing a comma, so it would look like this would print something like 1 comma 4 comma 9 comma, and let's say that was the end of our array. So it prints all elements separated by commas and an additional comma, right? Ah, yeah, there is a problem with that, and that is that notice that the body of the loop goes from here to here only because there are no braces. So what does it actually do? It prints all elements, and after it's all done, it prints a comma. Let's see how many people got that. And so that was answer C. And so the majority got that, but I did manage to fool a good part. Well, I knew what I was doing, actually. This time I knew what I was doing. I do fool myself regularly, but all right. So we fooled, almost 40% of the general population. Well, that's the American way, as we'll know tomorrow. All right. So here's a more interesting one. I see. All right. Okay, I'm going to turn it off in just a minute here. So, we're getting a pretty good distribution here. So let's look at number 3 first here. Accounts must be an array list. Why? Well, it could be an array. because the syntax of the enhanced for loop is exactly the same for arrays and array lists. There's no difference. And so you can't tell. It could be either. If it was a regular for loop, you could tell from the size versus length, but here you can't tell. It counts how many counts are overdrawn. Not really, right? Because it counts how many are not overdrawn. Now, you could argue that if it counts one, it counts the other. And I guess I would, I couldn't totally disagree with that. It gives the wrong answer if all balances are negative. That's a little tough because we didn't actually know what answer it's supposed to give. So you could argue that, well, I mean, clearly what this is supposed to do is it's supposed to count all of the accounts that are not overdrawn, right, that have some money in it. So let's look at number 2. What happens if this thing has length 0? What happens if there are no elements in accounts? Then counter was set 0 here, and the loop was never entered. So it is legal to have a for each loop where you happen to iterate over an empty collection. That loop simply is never executed. And so in that case, then counter stays 0, so that would be the right answer. And is that the majority answer? Well, it looks like the majority answer is not the right answer. The right answer was close, so let's hope that tomorrow it gets better. All right, I have a couple more minutes, and I saw a question pop up here, so how about I talk about that real quick? So someone was asking here about is sorted. So how can I find out whether an array is sorted or whether it's not sorted? So let's look at an example here. So let's say this is my array, 4, 11, 4, 5. So how do you know it's not sorted? You have to find this pair here, and you have to see that they're out of order. And so let's see what the fellow did in this case here. So here he said, if he finds a value that's less equal than its predecessor, he should return. And that sounds like basically the right idea. The way I would have done it is I would have said, if values I is greater than values I plus 1, but that's exactly the same thing, right? He checked for less equal, I checked for greater. Why do I check for greater? Instead of less equal? One less character to type. Right? Greater, 1 character, less equal, 2 characters. So after you've coded for a while, you have enough look ahead that you know that. All right. Where do you have to worry about? What is the danger in what I just wrote down? Yeah? So what's the danger? Why does A plus 1 make us nervous? Yeah, so you worry about, are you going to run out of bounds? And so that's the only thing that's to worry about. I think you can all do this by Wednesday. That was the draft, right? All right. I guess that's all I have. So since everyone is eager to enjoy the hot weather, I will see you next Wednesday for the exam, right? So this Wednesday there's a lecture. Next Monday is Veterans Day. Next Wednesday is the exam. And I will be here and personally deal with any network failures.